So let's consider the following system of two linear equations in the variables x1 and x2. So we have 2x1 minus 9x2 is 12 as the top equation. Equation number 2 is 4x1 plus 2x2 is equal to minus 16. And so there are various strategies that you probably have used in the past to solve equations, systems of equations like this. So for example, we could solve for x1 in the top equation and then substitute that into equation number 2 and solve for x2. I'm going to take a look at a method that's going to scale up nicely to much larger systems of differential equations. So another method that you probably are familiar with is what would be called like the elimination method. So how that might work is we can cancel out the term in this second equation if we were to multiply the top equation by minus 2 and then add that to the second equation. So minus 2 times 2, we add that here, that gives us 0x1. Minus 2 times minus 9 gives us 18, and then we add 2, which gives us 20x2. And the same here, minus 2 times 12 minus 16 gives us minus 40. And so the nice part about eliminating the x1 is now we just have an equation for x2, and we can solve for x2 by dividing that bottom equation by 20. So from this equation, we can see that x2 is going to have to equal minus 2, and we still have this equation up here. And so what you may be inclined to do is plug this in to the top equation and then solve for x1. That is a totally reasonable approach. But again, in order to come up with a method that might scale up nicer, let's consider doing the following operation instead. So instead, let's now take this bottom equation. We're going to multiply it by 9 and then add it to the top equation so that we similarly eliminate the x2 term in the top equation. And so after applying this operation, what's left up top is 2x1. Now we've killed off the x2 term and we have a minus 6 over here. And so now I can see very quickly what the solution will be for x1 as well. Just have one last thing, which would be divide this top equation by 2. So now I can see a solution to this system would be x1 is minus 3 and x2 is equal to minus 2. Okay, so we have discussed what a system of linear equations are. Now let's talk about what a solution to that system would be. So a solution is going to be an ordered list of numbers, as many numbers as variables that we have, so that when we plug in each of these values for each of the variables x1 up to xn, they simultaneously make all of the equations true in the system. So this is important. We want to make sure that when we do this substitution, every single one of the linear equations in the system is satisfied. So for example, on the previous slide, we saw that x1, x2 equals minus 3 minus 2 was a solution to this system down below. And it's always a good habit when you're at home and you've got time to make sure that these answers work. So if I take 2 times minus 3 and subtract 9 times x2, which is minus 2, you want to make sure that you get 12. And in this case, we do. And you also want to make sure that when I plug minus 3 for x1 into the second equation and minus 2 for x2 in the second equation, that we get minus 16. So both of those calculations check out. So we have just validated that we have found our solution. And there's a nice picture for those that are like to see what's going on, in that each of these two linear equations we could graph as a line. So in blue, we've got the top equation, 2x1 minus 9x2 is 12. So that looks like this. The second equation looks like this. And this solution is actually the intersection point of these two lines. So here we've got a system of two linear equations in terms of two variables. And notice that we have one unique solution, namely the coordinates of the point at their intersection. So the example we just took a look at, we had one unique solution to that system. Here are two additional systems of linear equations, two linear equations in terms of two variables. So let's consider this equation over here. Well, if you look at these two equations, it's actually just the same equation written two times, right? We multiplied the top equation by 2 to wind up with the second equation. So what we see is that if we wanted to graph these two lines, we're just graphing the same line twice. So here, these two lines actually are right on top of each other. So any point that's on one of the lines is also a point on the second line. So there's an infinite number of points that lay on both of these lines, and all of them would be a solution. So here's a case where we have an infinite number of solutions to this line. Not every single point in the plane is a solution, but we have an entire line of solutions. In the second system that we have over here, we now have multiplied the coefficients by 2, but we have the same constant over here as 10. So when we plot these two equations, what we'll see is that these are two parallel lines. And in fact, they don't share any points in common. So any coordinate, any pair of coordinates that satisfies this top equation is not going to satisfy this second equation because these are two different but parallel lines. So here's an example where no solution exists. So to kind of summarize the behavior that we've seen for these systems of two equations with two variables, it's possible that we have no solution, such as this system over here, where the equivalent, the picture would be two parallel lines. So when a system has no solution, we call those inconsistent systems. If a system of linear equations does have a solution, we call it consistent. And there are different things that can happen. We can get exactly one unique solution when the two lines intersect at one unique point, and that was the previous example. Or we can get an infinite number of solutions when each of the equations is just a repeat and the two lines are actually identical. What we don't see is getting exactly two solutions or exactly three solutions and so on. So if a solution exists, we either have a unique solution or we're going to have infinitely many solutions.